Section 5.4 is titled Dynamical Systems and Markov Chains. I'm going to explain the material using an example I found in this open educational resource. It's a linear algebra book by Nicholson called Open Linear Algebra with Applications. Okay, so here's the example. Assume that there are three social classes, the upper, middle, and lower class, and social mobility behaves as follows. Of the children of upper class parents, 70% remain upper class, 10% become middle class, and 20% become lower class. Similarly, if you have middle class parents in this model, a certain percentage of their children become upper class, certain percentage, 10% remain middle class, and certain percentage become lower class. And then we have a similar situation for lower class parents. Some of their children become upper class, some become middle class, and some become lower class. Okay, and so the question is, well, there's two parts, two questions. Find the probability that the grandchild of lower class parents becomes upper class. So we have some social mobility. And then part B says, after a long time, say maybe 20 generations, what will the breakdown of society be in terms of upper class, middle class, and lower class percentages? So here's how to solve this problem. So the first thing is to note that there's just three what are called states in general in this problem. So being in the upper class is one state, being in the middle class or being in the lower class is a third state. Now let t be a number that counts the number of generations. I chose t for time. And then let x1 of t be the probability or proportion of people in the upper class, or the probability that a person in generation t is in the upper class. Let similarly x2 be the probability that the person in generation t is in the middle class, and likewise for x3 corresponds to the lower class. And then form this what's called a state vector. Again, state refers to the three possible states, upper, middle, lower, in this problem. Other problems might have two states, 3, 4, or 5 different states or categories. So we form the state vector. And because each component here is a probability, it's a number between 0 and 1 inclusive, and they add up to 1. Again, you can think of probabilities as a proportion of people in the upper class, like maybe 70% of the population is in the upper class, and so forth. Okay, so in part A, we start with a person that we know is in the lower class. The parents are in the lower class is what part A said, and so their state vector at time t equals 0 is given by 0, 0, 1. The parents are in the lower class, and so that's why this is a 1. We know 100% certainty that they're in the lower class. Okay, now in part B, we don't know what the breakdown at time t equals 0 of x1, x2, and x3. In other words, we don't know what percentage of the population is in the upper class. We don't know what percentage is the middle and lower classes, but that's okay. It won't matter to be able to answer this question of, in the long run, what is the breakdown percentage-wise of the upper, middle, and lower class. Now, here's the key observation to make. At generation t plus 1, the probability that a person is in the upper class, say, is given by the following formula, which expresses the percentage or probability that a person is in the upper class. Remember, x sub 1 is in the upper, means the upper class, time t plus 1 is this, and then it's a linear combination of the probabilities of being in various other states. So 0.7 times x1, 70% of the upper class people at time or generation t become, or have kids, I should say, that become upper class or remain upper class. Then of the parents that are middle class at time t, 80% of their kids will become upper class. So their kids refers to or means generation t plus 1. Okay, and then for parents that are lower class at time t or generation t, 60% of them will have kids who become upper class, is what the problem said. So 60% or 0.6 times the fraction of people that are in the lower class will have kids that are in the upper class. So again, this is the key observation to make, is that, in other words, the probability of being in a certain state, in this case the upper class, at time t plus 1, is a linear combination of the probabilities at time t of being in the different states. One thing matrices are great at encoding is linear combinations. And so if we form a matrix, this equation here can be written as x1 of t plus 1 is equal to this row dotted with this column. So here's our state vector. This is what we call the state vector. And here I've just filled in the first row from this equation up here. And we can do the exact same thing for the x2, the middle class, at time t plus 1, and x3, the lower class, at time t plus 2. And so going back to the data that the problem gave us, we get this matrix times this state vector gives the state vector at time t plus 1. How did I get, or what's this column here say? That's coming from the statement that of the children of upper class parents, 70% remain upper class, 10% become middle class, and 20% become lower class. Note that each column of this matrix adds up to 1. That's because these are all probabilities that, for example, this first column, the probability that someone in the upper class with upper class parents becomes remains upper, becomes middle, becomes lower. So these all have to add up to 1 because one of these scenarios has got to hold true. So similarly, this adds up to 1. The numbers in this column add up to 1. And they're all non-negative entries because they represent probability. And so they're between 0 and 1, all of the entries. And then one thing that's not necessarily true is that the rows do not have to add up to 1. It's just the columns have to add up to 1. And any such matrix is called a stochastic matrix. Let's just rewrite our equation from the previous page. So let P be this matrix. This is called a transition matrix. And let x of t be this vector here, is sometimes called a state vector. And our equation can be compactly written as the state vector at time t plus 1 is equal to this matrix product of the matrix P, the transition matrix, times the state vector at time t. And this is an example of a Markov chain. It's any situation where the state vector x at time t plus 1 is a stochastic matrix times the state vector at time t. Now let's plug in t equals 1 into this equation. And so we see that x of 1 plus 1, so that's 2, is equal to the transition matrix times the state vector at 1. And then we know by plugging in t equals 0 that the state vector at 1 time t equals 1 is equal to p times the state vector at time 0. And so since matrix multiplication is associative, we get p squared times x0. In other words, x of 2 is equal to p squared times x of 0. Similarly, x of 3, the state vector at time 3, is equal to p cubed times x0, the state vector at time t equals 0. And in general, this pattern holds that x of k is equal to p to the k times x of 0. Now, with all that preparation, we can finally get back to the problem. So remember, part A says, find the probability that the grandchild of a lower class parents becomes upper class. So suppose the parents are at time t, some generation t, then their children are going to be generation t plus 1, and the grandchildren are going to be generation t plus 2. The parent state vector is 0, 0, 1, since they're lower class. And remember, x of 3, the lowest component, is the lower class. Then the children's state vector is x of t plus 1, and that's the matrix P times the state vector of their parents, x of t. And so here's the matrix P, here's x of t, and then when you do the matrix multiplication, because you're multiplying by this third standard basis vector, you pick out the third column. So this is what happens. Then to get the grandchildren state vector, that's x of t plus 2, and that's p times the x of t plus 1. And so here's p, here's x of t plus 1 that we found earlier. And what we get is, when you do the matrix multiplication, we get this. How did I get this first element here, or entry here? I did 0.7 times 0.6 plus 0.8 times 0.3 plus 0.6 times 0.1. It's row 1 times column 1, since this is in the 1, 1 position. And then here you can see I did the arithmetic out here. Now, part A is asking for x sub 1 of t plus 2, and so what we see that's exactly here, and it's 7.72 or 72%, and so that's the answer. That's the probability that the grandchild of a lower class parent becomes upper class. Then part B of the question says, after a long time, say 20 generations, although we'll see it's much sooner, like 4 generations or 5 generations, what will the breakdown of society be? So in Sage Math, computing powers of p, namely p squared, p cubed, show that these powers stabilize to this matrix. Here I've shown the code. So this here is p to the first power. That's our original matrix p. Then p squared is this, p cubed is this, and so forth. This here is p to the fifth. And you see that they basically stabilize. P to the fourth and p to the fifth are the same matrix, and in fact each matrix has the same columns, 0.696, 0.134, and 0.170. And then why are we computing powers of p? Well, remember that this formula here that says the state vector at time k is equal to p to the k times the state vector at time 0. So because this p to the k appears, that's why we're computing these powers of k. And we're letting k go to infinity, if you will, although it doesn't need to be even that large, as we've seen. Once you're at k equals 4 or 5, the matrix stabilizes. And so then this matrix p to the k is over here. It's a slightly different than the matrix p that we started with, because we started with something that was 0.7, 0.1, 0.2. But it's fairly close. Any case, here's p to the k is here, x0 is here, and so then when we multiply this, now first of all, we don't know exactly what these values are, but as I alluded to a few slides ago, it won't matter. We don't know what the initial breakup or breakdown of the population in terms of upper, middle, and lower class is, but because we know that the proportion, each of these proportions, collectively they add up to 100%, or as decimals they add up to 1. When we do this matrix multiplication, what we're going to do, this entry here is going to be row 1 dotted with this column 1. So that's 0.696 times this plus 0.696 times that plus 0.696 times that. And when you factor out the 0.696, it's 0.696 times the sum of this, the x1, x2, x3, but that sum is 1, and so you're just going to end up with 0.696. And similarly, here you get the second row, and the entry here is the entries in the third row. And so this is the answer. What we're saying is that in the long run, 69.6% of the population will become upper class, 13.4% of the population will become middle class, and 17% of the population will become lower class. And how long is the long run? Well, from these computations here, you can see that even after like p to the fourth, so if each generation is 25 years, 4 times 25 is 100, so after 100 years, but even after 2 generations, you're getting pretty close to the long-term behavior. Now, one question you might have is, well, why did that matrix stabilize, and how to find the answer without computing all these powers of p? In other words, how to find this answer without using Sage Math. Okay, so we want the long-run behavior. In other words, what is the state vector x of t stabilizing to? Because that will give the long-term breakup or breakdown of the population. So suppose x is what the long-term breakdown is for some x1, x2, x3. So these are actual numbers, or numbers or decimals that add up to 1. And then our equation, our Markov process equation again, when you take t goes to infinity, this x of t plus 1 tends to x. Again, that's what this line is saying. And then x of t just tends to this vector x. And what this then equation here is saying is that x is an eigenvector for p with eigenvalue 1. Again, the question is, how do we find this x? Again, the x is the long-term behavior of the state vector. Okay, so we take this equation, subtract off the x, factor out then the x in here, throwing in the identity matrix. And so x is in the null space of this matrix P minus I. Here I is the 3 by 3 identity matrix. And then when you compute that by subtracting ones off the diagonal entries of P, you get this. This here should be negative 0.3. So to find the null space of P minus I, what we do is row reduce to get, we row reduce this matrix P minus I to get this matrix here. Here I've shown the code in Sage to row reduce to avoid doing this by hand, which is what I recommend at this point. This first row translates to x1 minus 78 over 19 x3 equals 0. Here I've left off the augmented matrix, and so anyway, there's an equals 0. And the second row means x2 minus 15 19th x3 is equal to 0. This equation here says that x1 is 78 19th x3. This one tells us what x2 is in terms of x3, and then x3 is our free variable. And so incidentally, the null space is x3 times this column vector, where x3 is any real number. It's a free variable. It can be anything. And so this here is our eigenvector. But we've got one additional condition on this vector x that we want to find, namely that it's the sum of its entries have to add up to 1. These don't add up to 1. So we also need that x1 plus x2 plus x3 add up to 1. x1 again is 78 over 19 times x3. x2 is this fraction times x3, and x3 is just x3. And so now we can solve for the specific value of x3. Turns out to be 0.169. And then x1 is 78 over 19 times x3, which we now know. And so x1 turns out to be 0.694, and x2 is a certain fraction times x3, and computing that all out, we get 0.134. And this is exactly what we found out earlier using Sage Math, computing the powers of P. And so here again, I've just written the answer. The eventual breakdown of society will be x1 is what the upper class will end up being. So that's 0.694. So 69% of the population will be upper class in the long run. And then the middle class and lower class are similar. Middle class is x2 and lower class is x3.